And it's such an extraordinary molecule from the perspective of life, right? It is something that makes life on Earth possible. It's essential to all organisms, and humans have essentially learned to take advantage of this universal need for water, and we've been doing so for quite a long time. So what I'm going to give you a brief overview of here are some of those key characteristics, like unique physical and chemical properties, and what they mean to life on Earth. And so those characteristics we'll consider here are the high degrees of cohesion and adhesion that water molecules display. Water's molecule as a solvent, its ability to dissolve substances. We'll talk more about that. Water's ability to regulate temperature has a whole variety of different implications. Those unique physical and chemical properties mean that water expands as it freezes. So it's an exception to the rule that solids are more dense than liquid, right? This is why ice floats when you put it in a glass of water. So we'll discuss that. And then the just very important role of water participating in life's chemical reactions. And many of those chemical reactions that I'll reference are ones that are super important to organismal biology, photosynthetic reactions, other metabolic reactions that occur in the cells of plants and animals require water or take place in water. All right, so I'm just going to give you a brief overview of each of these properties. So starting with the first, let's define and clarify what both cohesion and adhesion refer to. So we talked about the nature of hydrogen bonds, and it's those hydrogen bonds that contribute to this property of cohesion. Cohesion is a term that refers to the tendency of like to attract like, all right? So water molecules sticking to each other, right? Water molecules being attracted to each other is described as cohesion. This is a fancy way to say that water molecules basically are sticky. This is significant here on planet Earth. Without cohesion, water would evaporate very rapidly from most of the surfaces in which it's found on Earth. And you've probably observed this in your everyday life. If you overfill a glass with water and you get just above the rim of the glass of water, but the water doesn't really flow over the side unless you kind of bump into it. That's because of that stickiness that creates a tension, especially at that surface. If you've ever had a leaky faucet, you'll notice that the water really kind of pools up before droplets of water fall off and eventually succumb to the force of gravity. Again, that's because of that stickiness, all right? So this means something special, essentially, for water. When this stickiness occurs at the surface, we refer to that as surface tension. And again, not all liquids do this. This is unique to water, and water has this high surface tension because of cohesion. So at this boundary between water and the air, the water molecules are forming hydrogen bonds with their neighbor kind of to the sides and below them in the liquid. And those bonds are holding that surface together. It almost creates like a skin, right? So that's why this insect and other types of insects, small animals, leaves floating on a pond, right? They don't break through the surface. That tension is strong enough that it can support, a certain amount of weight without breaking that skin or breaking that tension. So this water strider can kind of skate across the pond and it doesn't break through, okay? And once again, this is primarily due to those hydrogen bonds. Another molecular property of water is what we call adhesion. So this is kind of a related but different property. Whereas cohesion describes the attraction of like to like, so similar structures attracted to each other or similar substances. Adhesion describes the attraction of two different things to each other. So the tendency of water to stick to things other than water is an example of adhesion. So if water soaks into a paper towel, right, it's attracted to the materials of the paper towel. That's adhesion. If some of you are taking lab this semester, this is a property that you're studying in one of your labs that focuses on water, right? When you are learning how to, read the volume of a graduated cylinder. Sorry, terrible drawing there. You learn to read at the bottom of the meniscus. And the meniscus forms for two reasons, right? It forms because of surface tension. So this skin that forms at the top due to cohesion is the result of surface tension. But this curvature that you get of water in the graduated cylinder is the result of adhesion, because the water is sticking to the surface of the glass, and that kind of pulls it up the sides of a narrow tube. All right. So again, that's why you learn to read at the bottom of the meniscus for consistency. Okay. And both of these have, as I mentioned, kind of cellular consequences, but also physiological consequences. This is something we'll come back to later in the semester, but plants are able to transport both water and nutrients through their entire bodies without utilizing any energy, spending any energy, just essentially taking advantage of the cohesive and adhesive properties of water. This process is actually referred to as the cohesion tension theory. And it begins when water evaporates out of little pores in the surface of leaves, and that creates a tension. And that tension basically pulls on adjacent water molecules. But because of that stickiness, that tension gets transmitted from water molecule to water molecule all the way through the stem of a plant. That's how strong this force is. It's aided by adhesion, because the veins of plants, the xylem that this water is traveling through, are kind of similar to that graduated cylinder. They're skinny tubes. And so that adhesion is helping the water cling to the surface of those veins, all right? And this is, we're seeing a palm tree here, but even the world's tallest trees can do this and pull water up from the soil, even if that tree is a few hundred feet off the surface of the ground. So it's a really important physiological process. It's critical both to water transport, but also nutrient transport in plants. And plants can do that for free without spending any energy because of these unique chemical properties of water. Okay, so water is cohesive and adhesive. Water is also a really good solvent. So to say something is a solvent means that it's good at interacting with other substances, and more specifically dissolving other substances. So a solvent is a chemical in which other substances that we refer to as solutes dissolve. All right. So a solution consists of one or more solutes that are dissolved in a solvent. Okay. So solvent plus solutes equals solution. And again, there's a variety of different ways to make a solution, but water acts as a particularly good solvent. We tend to divide chemicals into two categories based on their kind of relationship with or affinity for water. So hydrophilic substances are substances that are either polar or are ions, which you'll recall from the previous chapter means they carry a charge. These are substances that are likely to readily dissolve in water. This term hydrophilic means water loving. So there's a natural affinity for water. This includes things like sugar, salt, and other ions. Electrolytes, right, are ions that we can find in our body's fluids. So if your salt tastes sweaty, if your sweat tastes salty, I said that backwards. That's an example of water's ability to dissolve those ions, those electrolytes. Often people will drink sports drinks, or other things like Nuun, electrolyte tablets that replace or replenish not just the water, but the electrolytes that are lost during exercise, in sweat, in perspiration. So things like magnesium, potassium, calcium, sodium that are needed for the regular sort of ionic balance of our cells. So not every substance, though, behaves that way with water. So some molecules are what we describe as hydrophobic. These are generally non-polar molecules. I'm talking ahead a little bit here, but I'll finish the thought. So non-polar molecules are ones that do not dissolve easily in water, or don't form those hydrogen bonds with water. Okay, but to back up for a moment, again, this tends to, ions make good solutes with water. So salt would be an example of a solute. Water, in this case, is acting as the solvent that helps to break apart the sodiums from the chloride. And when those dissociate in water, we have a resulting solution. In this case, of course, that solution is salt water. So as those salt crystals dissolve, polar water molecules, kind of surround each of the sodium and chloride ions to form that solution. Okay. Coming up in one of the upcoming modules, when we talk about the nature of cells, we're going to talk quite a bit about cell membranes, and we'll come back to this idea of hydrophobic substances. Things like butter and oil are hydrophobic, right? They're mostly made of carbon and hydrogen, and those form non-polar bonds with each other. So this is, why we need soap to wash our dishes a lot of the time, right? Water alone doesn't break up, oil or grease on your dishes or on your hands or your clothes. We use detergents to kind of dislodge those substances. So we'll come back to that as it relates to cell membranes and transport as well. Okay, another really important property of water is its ability to resist temperature changes. And once again, we can attribute that to those unique hydrogen bonds. So what this means is that water cools down or heats up very slowly. So for example, a body of water is going to absorb a lot of heat before its temperature actually rises. If you live in, coastal parts of Orange County or coastal parts of California, this is a property of water that you benefit from, right? Our proximity to the ocean, our proximity to a large body of water, is one of the reasons why we have milder temperatures than inland regions. And also why our temperature swings aren't as extreme, right? So we have overall milder temperatures, and we don't have dramatically different temperatures between the day and night. And the same is true of ocean temperatures. If you go inland, not only is it warmer, but in our deserts, there can be really dramatic differences in temperature between the day and night. It can be really hot during the day and really cold at night. So once again, we can kind of relate this back to those hydrogen bonds. So a more formal way to define this or describe this is to say that water has a very high specific heat. So specific heat is a property that describes the amount of energy that's needed to raise the temperature of a substance by 1 degree Celsius. All right. When molecules absorb energy, they move faster. And water's hydrogen bonds tend to kind of counteract or slow down that molecular movement. All right. As a result, more heat is needed to raise water's temperature than is required for most other liquids, including things like alcohol. All right. Again, if you're taking the lab this semester, this is something you either already have or will be exploring in lab. Temperature is just a measure of the rate of vibration. So again, if those hydrogen bonds are slowing down that rate of movement, it's going to take longer for temperature to rise. So if you apply heat to a liquid, the molecules bounce faster. That's what is ultimately increasing temperature. All right. But again, when applied to water, there's a restraining, a resistant of that bouncing, and temperature rises more slowly. So at a given temperature, water has more heat than most liquids. And I kind of spoke ahead with some of the benefits of living in coastal California here, but this is important on a global scale because it influences climate, right? It's why we in California have like generally good weather year round. We have the steady temperatures of the Pacific Ocean to help with that. When you get away from the ocean, not just in California, but even further inland in central United States, the winters are much colder, summers are much hotter, all right? And of course, this plays out on a global scale. So the ocean plays a big role in stabilizing the Earth's temperature as well. Okay, a neat property that also has biological implications of water is the fact that it expands upon freezing. This is very unusual. In liquid water, the hydrogen bonds are constantly forming and re-breaking. So if you recall from the previous lecture, we defined these hydrogen bonds indicated by the little black dashed marks here, bonding adjacent water molecules to each other. We pointed out that these are relatively weak because they're frequently breaking and reforming. And so in liquid, because that's happening so quickly, the breaking and reforming of those bonds, water molecules tend to be very close together in the liquid form. When water freezes, so in an ice crystal, the hydrogen bonds become more stable and the molecules basically get locked into place. So in that sort of crystalline structure of water in the frozen form, you have the hydrogen bonds forming such that there's the maximum amount of space essentially between adjacent molecules, all right? And it forms these roughly kind of hexagonal shapes like you can see here. What does this mean? Well, as the image here shows, it means that water is less dense in the solid form than it is in the liquid form. That is very unusual, right? For most substances, the solid form is more dense than a liquid form, right? So most solid substances that you would put in water, in a glass of water, are going to sink to the bottom of the glass, but not ice, right? Ice cubes float in your glass. And this is interesting to reflect on when you're, drinking an ice water, but it has really significant implications for life, especially for aquatic organisms. So when air temperature drops in lakes, ponds, other bodies of water, a small amount of water will freeze at the surface of the pond. And again, that stays on the top because it's less dense. So we have ice forming at the top of this pond here. It's not sinking to the bottom, all right? That kind of skin of ice, that cap of ice helps to retain water, helps to retain heat in the water below. If water were the type of substance that became denser upon freezing, right? If it was denser in the solid form, that ice would sink to the bottom. And then the lake or pond would gradually turn to ice from the bottom up. That would entrap organisms that live there. It would prevent organisms from being able to survive throughout the winter. Instead, ice is providing this essentially insulation, and life can persist throughout those winter months below the ice surface. Now, that's certainly a benefit in terms of aquatic ecosystems, but this can be deadly on a kind of cellular level. And so we'll talk about some really interesting physiological adaptations that organisms that live in particularly cold environments have to deal with this. But if the water inside your cells freeze, that can rupture a cell, right? So if, again, ice crystals form inside of cells, then there's an expansion of ice, and that can rupture cell membranes. It can kill cells. And so there's lots of adaptations to deal with this, found among different organisms that live in cold environments, extremely cold weather. A lot of those adaptations relate to just avoiding freezing. So mammals that have, a thick coat of fur, that have layers of fat, right, to kind of insulate those cells and prevent feeding. But there are some organisms, including some species of fish, that actually produce a type of antifreeze chemical in their cells that prevents those cells from freezing solid, and therefore, prevents that rupturing from happening. So once again, this is a great example of this kind of intersection between chemical and molecular properties and biological consequences. The final point here I'll make about water, in terms of its important properties, is its role in chemical reactions. So life exists, our cells function because of thousands of simultaneous chemical reactions that are taking place in our cells. And in many cases, these reactions are taking place in water, all right? We'll talk more about this, especially when we look at the chemical reactions involved in processes like photosynthesis and respiration. But these are processes that require water. Water plays different roles in these chemical reactions that we'll talk more about. But almost all of life's chemical reactions are occurring in this watery solution that fills cells, that cells are found in addition to, again, water directly participating. When we talk about photosynthesis, we'll talk about the role of water in donating electrons to an electron transport chain. So we're not exaggerating when we say that this is critical to life. And it's these chemical properties that give water its life-supporting characteristics. Okay, so while we are on the topic of water, I want to talk a little bit about pH, which, once again, I'm repeating myself, but this is another great example of the intersection between chemistry and biology, because a balance of acids and bases has really important consequences for cellular processes and for physiology. Acids and bases, which, as we'll see, the pH scale describes, play an important role in our everyday life. And you've experienced, very acidic food, or tart flavors, associated with things like yogurt or spoiled milk. If you've accidentally ever consumed that, that comes from acid producing bacteria. There's flowers whose pigments are sensitive to pH. If you have hydrangeas, you can sort of modify the color of those flowers by manipulating the pH of the soil. So again, these are principles we interact with in our everyday life. Our digestion relies on a certain acidity. Our stomach produces hydrochloric acid to kind of kill microbes to prevent us from getting sick from our food, activate enzymes that play a role in the digestion of food. So there's a lot of applications to an understanding of pH. So pH describes the concentration of hydrogen ions in water. So one of the most kind of important substances dissolved in water is one of the simplest, right? It's these hydrogen ions. And each hydrogen ion is a hydrogen atom that's been stripped of an electron. So when we see H for hydrogen with a plus sign, that's a hydrogen atom that's lost an electron. Another way to say that is it's at that point simply a proton, okay? So this is pretty simple, but having a balance of hydrogen ions in solution in cells is critical to life, all right? So one source of hydrogen is just pure water, right? So at any time you have about 1 in a million water molecules spontaneously breaking up into pieces. And when it does, it releases hydrogen ions and it releases hydroxide ions, which are, of course, the OHs, the rest of the atoms that make up the water molecule. So in pure water, those are balanced. So the number of hydrogen ions is exactly the same as the number of hydroxide ions. So that's what we would call a neutral solution. So you could count these up here, and we've got 4 hydroxides and 4 hydrogen ions, all right? We describe a solution as being either acidic or basic if that proportion of hydrogen ions to hydroxide ions is out of balance, all right? So in an acidic solution, there's a greater proportion of those hydrogen ions to the hydroxide ions, so more of these H pluses, all right? In a basic solution, it's the opposite. So if the concentration of hydroxide solutions outweighs or is greater than the concentration of hydrogen protons, that's what we refer to as a basic solution, all right? So I'm going to introduce you to the pH scale, and we'll look at a few more examples of this in a moment, but going back to some of the examples I already mentioned, right? So for acids, we could think about things like hydrochloric acid, sour foods like vinegar and lemon juice. Adding a hydrochloric acid to pure water would release those hydrogen ions into solution. Baking soda that you likely have around your house, sodium hydroxide that's used to like clean ovens, clean drains. Those are 2 examples of very basic solutions. So we can indicate this on a pH scale. And this is important to be familiar with because our cells rely heavily on a balance of hydrogen ions and hydroxide ions. So we use the pH scale to measure how acidic or basic a solution is. As you can see here, this scale ranges from 0 to 14, with 7 representing a neutral solution like pure water, where again, you would have an equal balance of hydrogen ions and hydroxide ions. The pH scale is a logarithmic scale. So that means with each unit on this scale, there's a 10-fold increase of the concentration of hydrogen ions, all right? So what this is actually measuring is hydrogen ion concentration. So a solution with a pH of 4 is 10 times more acidic than a pH with a solution of 5, all right? And 100 times, there's getting messy here, but if we go from 4 to 6, that's 100 times more acidic. If we go from 4 to 7, that's 1,000 times more acidic, all right? So each unit is multiplied by 10, all right? So at the low concentration end of the scale, these are the solutions we would refer to as basic. We've got things like, strong bases. Bleach is around a 12.5. Ammonia is around 11.5. Your average soap is around 10. laundry detergent around 9. I mentioned baking soda before, that's around 8.1. Okay, so this whole portion, or substances that fall along this portion of the pH scale, we would refer to as basic or alkaline. All right, and the higher the pH, the stronger the base. Okay. In the other direction from neutral, we get into, of course, acidic substances or solutions. Milk, our saliva actually is just like slightly acidic. It's pretty close to neutral. Our urine is slightly acidic. Rain is around like 5.7. The acidity of rain is increasing, especially in more industrial areas. Coffee is around a 5. Tomatoes are fairly acidic, around a pH of 4. And then you get into things like, again, vinegars, lemons, our stomach acid, acidity is around 1.6 to 1.8. Hydrochloric acid is a 0 on the scale, so very, very acidic. Okay, so a range of values here from basic to acidic. This reflects hydrogen ion concentration. And again, the key in interpreting this scale is to understand it's a 10-fold difference. So the entire scale is covering a wide range of acids and bases. All right, so low pH, high hydrogen ion concentration. High pH, low hydrogen ion concentration, right? So you're going to have more hydroxide ions down here, fewer hydroxide ions up here. Where this is, once again, one of those principles that we're going to continue to reference and return back to, because there are a whole lot of applications to understanding a balance of we're understanding the pH scale, understanding the balance of acids and bases, from a physiological perspective. We introduced homeostasis as one of the properties of life, right? This is one of those processes that our cells need to maintain homeostasis with respect to, and our bodies very tightly regulate the pH of our blood, the pH of our cells. So most organisms are maintaining a pH, pretty close to 7, not exactly. And for most organisms, if you stray too far from that, it could be lethal. So we need a system ultimately that helps us with managing the balance of hydrogen ions and hydroxide ions. Our blood is actually slightly basic. So a normal pH range for our blood is between like 7.35 and 7.45. Usually kind of 7.4, but it can range around 7.4 within that range. But that's pretty much it. So even a slight imbalance of your blood pH will make you very uncomfortable, could make you very sick, very, very irritable, and can cause some pretty significant problems. Decreasing blood pH, can lead to coma and ultimately death. So our body regulates this with the use of buffers. So buffer solutions help to maintain constant pH and prevent us from straying outside of that range by taking advantage of solutions that can release hydrogen ions if pH is too high, or absorb hydrogen ions if pH is too low. So in response to any potential changes, that's what will happen. These numbers are a little bit outdated here. It's really more around 7.4, as I said a moment ago. So this is super critical, and we'll talk more about this later in the semester, but the ability to maintain a steady pH in our blood is actually linked with our respiration. And so I put this point here at the end here in terms of the relationship of breathing to this. If you hold your breath, you're preventing the release of carbon dioxide, and that builds up in your blood. Carbon dioxide, when it dissolves in water, converts to carbonic acid. The body senses that change in pH and then triggers you to breathe, right? You can't just hold your breath and die. Your physiological systems will force you to take a break. So the maintenance of our blood pH specifically is tied to these physiological processes that we'll talk about later in the semester. And our survival depends on this. So if we didn't utilize this kind of buffer system, a glass of lemonade would kill you. I have this photo of of water here because, there are some people that are interested in drinking alkaline water, right? So this particular bottle is advertising minerals and electrolytes. That's a separate issue. And if you have an electrolyte deficiency, that can be really useful to address and replace with electrolyte enhanced water. But if you drink 8.8 pH water, it's not going to stay that way in your body, right? Your body has buffers that are going to neutralize that. So there's not a whole lot of good, valid, well-supported scientific evidence that there's any benefit to drinking these types of alkalized products. Okay, so I'm going to end this recording here. I've included you